So this notebook is running on my Spark cluster on Azure Databricks, and I've already gone through the process of installing the ArcGIS Geoanalytics engine library into my cluster. But first up in my notebook, I will need to import the various Geoanalytics engine libraries that I need to extend Spark to work with additional data sources, but also to give me access to the large range of spatial tools and functions that I'm going to be using in this workbook. I'm going to be working with Vic crash data from DTP. This is provided in a WGS84 coordinate system, and for this particular project, I will need to do the calculations and persist the downstream outputs into Vic Grid GDA 2020. And Geoanalytics Engine provides not only full coordinate system support, but actually gives you some help on picking the right transformations to use when jumping between GDA 94 to GDA 2020 or WGS 84 to GDA 2020 datums. And in Australia, this is particularly important because it includes the conformal and the conformal and distortion transformation grids for you to pick and choose as required. We're going to grab that data, transform it using ST transform, and because this is spatial temporal data, there is a time field that we need to tidy up and define that on the data frame. And then we want to filter the area of interest down from Victoria to Greater Melbourne, and this is where we tap into a feature service. We go to the ABS ArcGIS Online account and grab their Greater Capital Cities statistical areas, and essentially pluck out the Greater Melbourne boundary and use that to filter our crash data down, which is, if we quickly use an ST plot, we can see that crash data in a quick preview there. First analysis tool we're going to use is the simple aggregate points to create a time-stepped aggregation. And look, Geoanalytics Engine supports aggregating data into the excellent H3 spatial index, but H3 does rely on your data being in WGS84. So in this instance, we're going to create our own 1 kilometer grid in GDA 2020 Vic grid with a 1 hour kind of time slice. And then we're going to surface those results back into our GIS as a feature service, then allowing us to visualize that output. Again, we can visualize it in the notebook as a kind of an ST plot or using the ArcGIS Python API. In this instance, we are just looking at it as a feature service that we've persisted back to our GIS. And that includes not only the count, but we also created a summary statistic there to also, for this particular time slice, work out the total number of persons that were involved in crashes in that window as well. All right, moving on. Next one, instead of building your own user-defined functions, Geoanalytics Engine essentially brings a whole range of proven spatial stats tools like the hotspot analysis, which is very useful with crash stats data. This identifies statistically significant hot and cold spots and aggregates them into bins of whatever size you like. In this instance, I've been fairly quick on the settings, but 1,000-meter neighborhood distance with a time step interval of 2 years this time. And again, persisting that back into the GIS to give us this view of the Greater Melbourne area and how crashes change over time. And there are some cool spots in here as well, which again gives you kind of a citywide view of where some of these patterns might be changing over time. Yeah, that's the hotspot analysis tools. Okay, so the next one, and this is probably more, I find more important with crash data, is actually aggregating it back to road segments themselves. So for this one, we're going to do a spatial temporal join. You can perform joins either with spatial functions and Spark SQL, or in this instance, we're actually going to use, again, one of the tools, the spatial temporal join tool. Essentially, we're going to count the number of crashes that are within 15 meters of each road segment. With Spark SQL, you would use the st_d within function to achieve the same result. Again, push that back into our GIS, and we can then see all of those crashes that have been counted up against the road segments. And this is kind of useful because you can, with a bit more effort, you can start to have road crash rates and a time-stepped aggregation to see how that's changing over time. In this case, we've just done it for the entirety of 2022. And yeah, it starts to give you that kind of better view of it at a road segment level. Geoanalytics Engine also has intelligent tools that allow you to snap GPS data to road networks, and even taking into account things like the direction of travel and the bearing. And again, with more time, and if this was a proper study, we should probably have done that before just doing a spatial join. Clusters is another one. So if we just look at this time-aware data set over time, you can see quite clearly that there was, during the lockdowns of COVID, as you'd expect, there was a decrease in the number of crashes that happened during those lockdown periods. And so if we then filter it down to two of those particular lockdowns, so lockdown number 2, which was 111 days, and lockdown number 6, which was 77 days, we can then run a find point clusters on each of those two separate data frames. In this instance, for crash data, we typically use dbScan, which finds clusters of points that are in close proximity based upon a search distance. And optionally, you can also include a time window like a peak rush hour. And in this instance, instead of surfacing it in the GIS, we're just going to use stplot to look at those crash clusters and how they differ between those two different lockdowns. And again, you could do further downstream analysis of why these might be different, or again, persist them into the GIS for others in the business to make use of.